In case that happens, I prepared several other talks, but my computer is no longer accessible. I promise you, it'll be very entertaining. It's all worth it. Good. Very good. Okay, so the work that I will tell you about is something that I've been doing in the last 2-3 years, mostly over the pandemic. It's really also not the main thrust of the research that I do, but it's an interesting question nonetheless, which I've found a lot of fun working on. So the sort of broad motivation why I will tell you what I will tell you about is, recently we've seen gravitational waves, we've seen EHT, and there's a very clear sense that the next few years and the next few decades, there'll be an emerging field of what we should call gravitational spectroscopy. We observe black holes and we can measure various properties of what we should really call ultra-compact objects, not necessarily black holes. So this question, this perspective and this coming age, at least for me, sort of who usually works on very formal quantum field theory and holography sort of ideas, raises a very basic question: what is the spectrum of ultra-compact objects in theories of gravity, right? Does all of this new observational windows offer any hope of seeing anything? And if so, anything beyond what we know in GR, and if so, what's possible? Okay. So that's a broad question. So as soon as you ask this question, and coming from a background in string theory and supergravity, there is some answer, which is that in all of our study of gravity, especially in string theory, we know that there are coherent configurations. Right? So if I have any quantum theory, there are coherent states, and coherent states usually admit some classical description. And in fact, the fact that there are coherent states in string theory and gravity is what really has led to the holography revolution, right? In holography, we build solutions that are smooth, that describe specific states in supersymmetric configuration, but those you should think of as states that are coherent enough that they admit gravity, they admit constructions in classical theory of gravity, but they're genuine quantum states. So there is a precedence of thinking about coherent configurations of gravity already from string theory, but in all of those framework is supersymmetric. So the question that you want to ask relating to this new age of astrophysics is, can you actually genuinely have coherent states of quantum gravity exist beyond the supersymmetry regime, something that might actually have a chance of showing up in the real world? So that's the broad motivation of this thing. So in particular, as soon as you ask this question, what you want to understand are solitons in gravity. Okay. Solitons in gravity, lumps of objects that sit there, that are stable, that have finite energy density with no singularities whatsoever. And since these have to come from some theory of quantum gravity, you want them to be classically stable, at least. And you also want them to be somewhat metastable under quantum. I mean, you cannot expect them to be exactly stable under quantum fluctuations, but you want them to be at least metastable. There is some saddle which they sit, but they can decay to other things. And all of these things actually have a chance to make this whole picture quite rich. So the main issue, of course, in trying to find solutions in just run-of-the-mill gravity theories of this kind is, first, there's a big issue, which is that the reason why we were so successful in supergravity and string theory and making all of these things and learning a lot about gravity, holography, and black holes is because we had supersymmetry, and supersymmetry equations are linear. Right? They're not linear, well, they're first order. Equations of gravity are first order, so then we can solve them and we can say a lot. But once we give up supersymmetry, you get fairly nonlinear PDEs in Einstein's equation, and we've all seen them. And really, there's no hope, right? Then you should just give up if you don't know where you're going. Another issue, which is quite important for what's to come, is that if you want solitons in gravity, there are various no-go theorems that go back all the way to 1918 that tells you if in 4 dimensions, if I want something that is asymptotically flat, topologically trivial, and globally stationary just means that you have a time-like killing vector and you don't have any horizons, then it must be flat. So there's a no-go theorem that tells you you actually cannot have solitons that are lumps of matter and energy sitting there in just pure theory of gravity. You can build things that are called like boson stars and so on, but that requires some scalar matter and then have some other properties. Even though those, now we also know they're not physically viable object we should expect to see in the sky. So one way you can sort of move forward is if you have a no-go theorem, what it really tells you, wait, go ahead.
The no-go theorem is valid in pure gravity or gravity with matter or Benson energy conditions?
It's pure gravity. So for example, if I have gravity with scalar, there are boson star constructions. You can even make them classically stable, but they have nonlinear instability. That breaks them apart.
Sorry, how does just a black hole violate
globally? It has a horizon.
Okay.
Right. So it has a horizon. So we should not, we should think of a black hole in space-time as actually the thing that tells you GR is breaking down. Right? So it's beyond resolving a black hole requires something beyond.
So topologically trivial means also free of singularity.
So well, singularity and topology are different. You can have topology.
Then you have to add. I mean, you can have horizonless singular solutions.
Right? You can have horizonless singular solutions, but that's also bad. That's nonsense.
Yeah, but it's not in the hypothesis.
Well, so you mean here? Here? So asymptotically flat, topologically trivial. Yeah, the assumption is that it is smooth and
because in particular in the you mentioned the Einstein theorem in the 40, which is in 1941, and this is one of the hypotheses. Singularity free also.
Yeah. So the previous slide said we want a soliton where you can trust the solution everywhere. There's no singularity, where I know the full space now. I don't need extra physics to understand what it is. Okay. That's the goal. Good. So from this, so how can I avoid these no-go theorems? One obvious one, you should have some interesting topology. So we have to figure out what that should mean. And you should add something in your space-time. The simplest thing you might try adding is Maxwell fields, right? So we are used to thinking about electrodynamic systems, and minimally allow me to do that. You can have other sort of more interesting gravitational interactions like topological interactions, but I will not worry about that here today. But one critical important of what you will need if you are ever going to build this is going to be extra dimensions, and I will try to explain why that's going to be important. So
is adding any of this enough, or you sometimes need to take combinations?
So the first question of how adding interesting topology, if I just take the 4D space,
the ALE will be sufficient. You consider ALE solution.
That's in Euclidean space, right? That's not in Lorentzian space. And then if I add, so already if you just ask 4D, I want to put some interesting topology. That's very hard, and you can't do it. And then if you have some topology that's sitting there, as you know, you need something to support it. So the thing that you would need to support it is at least some Maxwell field, some magnetic field, some electric field, right? We know that you cannot have topological structure without something to support it. And then why the extra dimensions? It'll be clear why. The reason why you need extra dimensions comes from the following fact that we know, just pure geometry, is that if I have a region of interesting topology, let's say I have some cycle sitting there, some bubbling structure sitting there, we know in geometry, those object can be described in the near geometry region as a place where a circle shrinks, an extra dimension shrinks. This is a fact of topology. If you have a near a zero section of some cycle, you have an S1 that has to collapse. Okay, so this is why I want an extra dimension if I want to have something interesting topology. So if I want to build what I want to build, then the minimal sort of playground that I should look for, I take my 4D spacetime and add a bunch of circles, some Kaluza-Klein background with some magnetic field, and ask what I can do. Okay. And the picture that you could have in mind of what could happen is that you have some locus in spacetime where these extra dimensions are collapsing to zero size. You have an extra dimension that's collapsing to zero size. So this seems a bit odd to say, but all of you are familiar with this notion. So if I take, for example, a cylinder of this kind, this is something that is well defined, but I can add topology in this one-dimensional object by, for example, turning it into a cigar. Okay, so this is topologically distinct from here. But in doing so, here, at the end of the region here, you have a circle that's pinching off. Right? So this is the sort of intuition that you should have when you can get interesting topology. If you start pinching extra dimensions in some regions, then you have interesting topological structure. If you do this in higher dimensions, the space-time becomes much more interesting than just split into two pieces. So intuitively, have this in the back of your mind of what I mean in having some topology. Okay, so that's broad perspective of what we do. So let's see how we can build these objects. So I will pick a more specific playground, which is perfect. So I'll pick something specific, and then we'll try to set up the problem and see how far we can go. So I will take 4D space, and it's asymptotically flat, and then I have two circles. I have one circle here, and then in this 4D space, I have another circle, or Y2, and then I have my time that's out. So the time in this 3D base makes some four-dimensional space, which asymptotically is flat. We are going to assume this to be axially symmetric spacetime. And since this is a theory that I'm giving you in 6 dimensions, the minimal sort of ingredient that I could add to start to make this interesting, I'll add some free-form flux. And what this free-form flux does, it just turns on magnetic field onto your spacetime. It allows you to turn on magnetic field into your spacetime. So one observation that we made a few years ago is if you take this background and you study Einstein's equations in this background, you find that they're in their full nonlinear glory is that they decouple into sectors. Right? They decouple into a sector which I'll call reduced Einstein equations. So there is some other equation here, and then you have some last one which determines what the base looks like. So this is a base space, so it's determined by this. And if you solve these other fields, then this last one is determined. So this already is quite interesting that we take Einstein's equations in this 6-dimensional space with all of these fluxes. You see that it decomposes into sectors that don't talk to each other.
So you're talking about Einstein equation in 6 dimensions, or are you talking about Einstein coupled to some two-form gauge field?
Yes, it's Einstein with the Maxwell field, with the Maxwell field.
The two-form gauge field.
Yes, it's a two-form gauge field. If you reduce it on the S1, it's a Maxwell field in 4 dimensions. So the first observation is that if I write a metric ansatz that is sufficiently clever, you observe that Einstein's equation split into sectors which each have some interesting physical characteristic. So to tell you a bit more what these sectors do, so this one is just a Laplace's equation on the 3D base. So this we can understand. Then you have these other warp factors and their associated magnetic flux that goes with them. Here are what the equations look like. the main observation here is that if I look at each one of these sectors, it's the same equation that you would get by just taking vacuum Einstein's equation in 4 dimensions. So in some sense, this 6D theory is decomposing into pieces which each look like 4D vacuum Einstein equations. They're still nonlinear, but the thing that is exciting about this is that those equations that I just showed you, they admit integrable structure. They admit what is called the Gerhardt group, and there's a lot of integrable structure in them. There are various methods that existed from the 70s and the 60s in solving them. And in fact, many of the all the well-known black hole solutions are solutions of those equations. So you have the Kerr, you can describe with this, all the black hole solutions, all the black Saturn solutions you can describe. But the key point here is that those equations, although they're nonlinear, they're integrable. And there are a lot of techniques that exist in solving them. For our case, actually, we first spent a significant time studying those equations. We find that there are clever solutions we can construct. And in the first couple of papers we wrote, we thought the papers were solving the equation wasn't the main goal, but we thought we had clever ways of solving Einstein's equation in a new way. But then a couple of years later, we found that there's 60, 70 papers that had this structure. And the reason why they had it is precisely because these are integrable. You can map them to other types of problems, and when you do, then you can reconstruct the solutions that you want. Okay, so with that said, so then I have a machine that allows me to solve each one of these sectors of my problem. Then to construct what I want is a question of boundary conditions. For example, if we go back into this metric, I want to be able to shrink my circles as I wish, and I don't want to have a horizon. So this tells me that if I look at the combination in front of the time direction, this could never vanish anywhere. So that's a boundary condition. But already you can start to see this is going to mix one sector with another sector. Okay. I want to be able to shrink, let's say, the Y2 circle. Then I want this warp factor Z2 to go to infinity so it can collapse, while keeping Z1 there to be finite, so I don't have any horizon, and similarly here, right? So now I have a machine that solves different sectors, and then I can implement boundary conditions, which will then be where they would couple, but those coupling would be at an algebraic level. Right? So, okay, so now we can do this, then we can start to build solutions. So let me tell you what things look like.
Do you have to impose some conditions on the vanishing to avoid conical singularity?
I'll come to that. So if I give you equations, I want to understand sources first. So first, if I look at the ZH sort of a pair, these are used to having point-like sources. So those point-like sources, when we go back to supergravity and string theory, those are the things that give us BPS structure, right? They give us BPS structure that we use to think about. However, there is some other interesting sources that you can have here. Instead of having localized sources, you add sources that are rods, like segments of this kind. So meaning that there is some delta function that appears on the left-hand side of these equations along these rod segments. Okay? So when I consider those sources, there are very physical and interesting things happen, which is the following. I could have, for example, one of these rod sources where the direction that I collapse is a time direction, right? So d by dt has 0 norm. But whenever a time collapses, that's when I get a horizon. So if I have a time direction that collapses, then I get a horizon. So you can have a rod source where you get an actual genuine horizon as you want. But in the same vein, if I have a rod source where instead of collapsing the time circle, I collapse one of these extra dimensions, so let's say y1, what you get is some bubble. You get a finite size bubble. Instead of a horizon, what you get is a finite size bubble. The thing that is interesting about these bubbles, when you collapse a space-like direction, there are going to be smooth ends of space-time, which are geodesically complete. Okay, so you can have a finite size bubble in space-time where a geodesic can come and then bounce back, and the space-time is going to be completely smooth. And that's what we call a cycle. So it's a space of non-trivial H2. have the 2 cycles sitting there, which is stabilized. So in the construction that we have, each one of these bubbles, they could also have flux that's wrapped around them. And what that does, it gives them an effective charge. Right? In fact, one way you can think of magnetic black holes with monopoles, you can think of as black holes where you wrap flux on them. Okay? So you can wrap flux on each one of these bubbles, and then far away, this is going to look like an object sitting there with some magnetic charge associated. Any questions? Another thing you can do, so since now I told you that I can collapse extra dimensions, also the time circle, you can also collide these bubbling regions on top of each other. So you can make bound states of these bubbles that look like that. That's just a picture of this. And in this bound state, what you should have in mind, there is a region here, for example, this one where you have a horizon cap. You have a horizon cap, but then that region where you would have a horizon ends, and then you get a region where you just have a bubble where space-time smoothly ends. Exactly in a picture like this, so a geodetic would come in and it would bounce back. And then you could have multiple versions of these things. And then to get what you want, which is completely smooth, is you do the following. You can consider a chain of alternating rod sources, where what you do is, along this chain, you successively collapse the extra dimensions onto themselves. And what you get from the perspective of the 4-dimensional spacetime, you get a very large bubble, which is fat, where space-time smoothly ends, and far away, this thing is going to have interesting properties. So the geometry that we construct, for example, by picking sources of this kind, and you can make it as long as you want, is going to be completely smooth with no singularity, with some magnetic field that's attached to it.
So when you bounce on this bubble, do you come back to the same space or to another branch?
No, it's one branch. There's no multi-branches or anything of this type. It's the same space-time. I can tell you a lot of properties of that, but I have some backup slides if you want to ask me about more about the properties of what happens when you try to bounce. So you can construct this large chain of these bubbling sources, and then you get a solution which has no curvature singularities and have no horizons, and it's completely smooth. When you Kaluza-Klein reduce to 4 dimensions, what you actually get is a 4-dimensional black hole, which is actually symmetric in some magnetic field, but instead of having a horizon, it's a horizon that is singular, right? So this is a sort of an effective realization of what you might call a firewall in 4 dimensions. So if you look at it in 4D, what you get in this bubbling region, you get a black hole, which is singular at the horizon. And from a 4D perspective, when you're far away, you can't tell. All that you imagine seeing is a black hole, and we will see more pictures of this later. Okay, so I can tell you a couple more properties of this specific model.
So I'm a little bit confused. So as a 4D observer, if I actually did an experiment and had 2 of those things orbit, they would behave like black holes?
Yes, I will tell you a lot more about that in a moment, I promise. And I'll show you pretty pictures. It's rare that I get to do pretty pictures in anything I do. These are pictures that I'm very proud of.
So
Although I didn't make them.
So the radion or whatever, when you reduce to 4D, there's some singularity and it's stress energy at the horizon.
Yes, so that's right. So in 4D, you get an effective theory, which is going to be Einstein-Maxwell with scalars, with some scalar modes, which is just the radiance of the extra dimensions. So the stress tensor of those blow up at the would-be horizon. But what it's really telling you is that this thing is not that the system, from a 4D perspective, you say, oh, I'm done, it's singular. But really what it is that you don't have enough degree of freedom from the 4D physics to actually resolve that. But if you go back to higher dimensions, then you do. This really was telling you, if you're a 4D person, you come to this object very close. At some point, you should start to see 6D nature emerge.
And the curvature at 60 is less than the 60 Planck scale.
You can make these big. Well, I'll tell you a little bit more how you can make them big. So one specific example of this model is in order to exploit this integrability structure, depending what you want, the system could be significantly more complicated than one or not. But let's consider a class where so each one of these rods have some mass parameter associated with them, right? And have some charge associated with them, which is the value of the flux there. So if we can consider a set of a sequence of rods where the mass to charge ratio is fixed. So when you do this, the equations admit some integrable structure, which allows me to even solve even more. And you can write down an explicit solution to study. And in this case, you can check various things. So once you then write down a specific solution, the thing that is left for you to check is the regularity condition, as you were asking earlier. So there'll be some regularity condition to make sure that the space-time is smooth when you come here. And the way you think of the regularity condition is that I'm taking these rods, which are gravitating, and I'm stacking them on top of each other. So there is some balance force that I have to have between them for them to stabilize. So what this does, it gives you a bunch of algebraic equations. Well, only differential reduces these balance force equations are algebraic, and then you can, they're algebraic of order n. So if I have n rods, then you get n order polynomial. So it's hard to solve by hand. But if you take a large n limit, then you can actually solve those equations completely. For example, in one case, you can solve the system where each one of these rods, they kind of push each other. They stabilize to a point where the mass contribution of each rod will scale as n to the minus 3/4, where Ry is a characteristic unit that fixes the units of the whole system. It's the size of the extra dimension far away. In 4D, you can compute the ADM mass of this object, and it will scale as n to the 1/4. So you can be very explicit, and then each one of them have two magnetic charges, which were just a consequence of the system that we were studying. So these things, from a 4D perspective, are going to be ultra compact, and their sizes is less than twice their would-be Schwarzschild size. So they're very compact objects, as you might think. There is a bound of how large you can make n, right? Because if I have these rods that are gravitating and they're pushing each other, and their size is scaling as n to the minus 3/4, if I make n large enough, at some point they will approach the Planck limit, and then I can't make them very big. I can't make n grow anymore. And you can, funnily enough, you can sort of estimate what is the size of an object from which approaches the Planck bound. So it would be a sort of a star sitting there, which is like asteroid size mass. So easily asteroid size objects which are indistinguishable from a black hole. So there are a couple of funny properties of these solutions that I will describe. So this is a question of now, what does this look like as you approach it? So if you look at these bubbles and you just are in a region immediately outside, this is given by taking the radius to be 2m, where 2m is roughly the total mass of this object. And there is a correction of given by n to the half. The space-time dramatically simplifies. The space-time right outside here dramatically simplifies as compared to the actually bubbling structure that's sitting there. And you can actually explicitly write down the metric into this here. And it turns out this metric itself, it has a singularity on its own at r equal to 2m. So you think of the full 6D object as resolving this singular background. Okay. So you can write it. And this solution on its own exactly solves Einstein's equations, which was rather surprising. And one of the things that we discovered along this line is that let me get to that point. But before I tell you that, one of the things you might want to characterize on this solution is, so if we go back here, you have this thing where you have all of these rods, so it looks like very elongated. So you would imagine this is something that is incredibly, that has a very large dipole, right? And you know, there's an elongated sphere object there, you would tell. But one of the sort of magic that happens, which can actually be seen from here, is that when you're right outside this thing, there is a correction that appears here, which is this cosine of theta, right? There's an effective dipole moment, but this is not very large. So the deviation from actually it being spherically symmetric is fairly small from the outside point of view. Okay? And one way you can sort of characterize this is the following. If you imagine looking at a giant sphere that's surrounding this object, and you compute its area, and you compute this area as a function of r as you come closer and closer to the object. What you find is that the area of such a sphere is going to scale, as you might expect, as r squared. It will not have any sense of this extreme distortion that you might find. And until you come very close to this object, by very close is here. So here there are two dots. One of them, the dotted line is what you get by approximating using the approximated metric. And the colored line is the area of these spheres, is surrounding sphere as a function of radius in the actual spacetime. So at some point, the singular spacetime, those areas will blow up because it's singular. But the smooth spacetime, it ends smoothly at this bubbling structure. And along this curve, this thing looks very, very spherically symmetric with a small dipole. Right? And you wouldn't be able to tell until it comes very close. How close? So this is n is 20, just n sequence of bubbles. We have r over 2m this is the scale by which it starts to deviate to see what it is. And then when it deviates, you observe something dramatic happens, that the area of these spheres just grow very dramatically. So what's happening is that, so when it deviates, the area of these spheres become very, very large. So the spacetimes have what we call a bag-end structure. So as you're coming in, as you approach this object, it looks like a more or less spherically symmetric object with some dipole, and then you get hit a minimal surface, which is less than twice the Schwarzschild radius. And then once you go past this surface, it just blows up and opens up into this huge object that you couldn't tell from the outside. This is, we call it in spacetime, the back end. Any questions?
Oh, sorry, I was just, that's the Hobbit.
Yeah. Yeah. Pierre, who is the postdoc that I did this, is a big fan of Hopkins. So yeah, so basically it's almost some portal where you come in, this thing from outside looks like a black hole object, and you come very close, it just opens up to something which is smooth and have a lot of data associated with it. Okay. So so what do they do more formally? So in 4 dimensions, whenever I do a Kaluza client, these are generally singular solutions, which just means that you have to go to 6D to resolve them. But even in 6D, there is something funny that happens. We observe that there is a process by which you can take all of those rod sources and smear them in some way. And then when you do, you get a family of singular solutions that you can construct in the 6 dimensions, which are completely well behaved and have all nice properties that you might imagine.
Sorry, can I ask you something on these solutions that they open inside? What about the redshift factor? So you can go all the way going back without infinite time?
Yeah, that's right.
Coordinate time.
Yes. So I'll describe another class, and then I will actually show you more specific plots that shows you how, like how Like these are very, very weird things, but it's very hard to tell them apart from a black hole. Well, they're not weird from a stringy. We're used to playing with these things. Okay. So you actually find there's a family of singular solutions in 6 dimensions, which you can reduce to 4D, and they capture very well these geometries from the outside, where basically there is this bubbling structure just end up resolving something that looks like a smeared. Okay. So I'll switch now to another example. So that was one class of example that was fun to study for a while. So, but that example that I just showed you is a solution which it was nice, it was interesting, but it has fat magnetic fields. And for various reasons, you might not like that. Right? So it was a very good example to study in the classical in Einstein gravity beyond supersymmetry, but they had fat angular, large magnetic field. So you could ask, can you construct something that actually genuinely looks like a short shield black hole far away? Okay. So this would be a sort of first example of a smooth solution, which is not distinguishable, which is indistinguishable from a short shield. So I'll call this short shield soliton, where you have some net neutral charge. The way you might construct this is you look at the bubbling solution. You can construct a bubble which has 0 charge. In fact, a single bubble which has 0 charge is the same thing as the Witten bubble of nothing, for those people who know. A single bubble with no charge is just a Witten bubble of nothing. But to first order, you can think of each one of these bubbles as taking those bubbles of nothing and just adding charge on top of them. And the value of adding the charge is what stabilizes. So you can imagine constructing a solution where you take, for example, 3 bubbles, and then you have a charge Q, minus Q, and a charge Q in the bottom bubble. In fact, there's a large family we can construct where we have 3 bubbles where you have different charges sitting on the opposite side, but we can tune these charges so that they cancel. And if you can construct such a solution, then it would be something that looks like a short shield far away with a dipole magnetic field, right? With a dipole magnetic field. So you can ask, what does that do? What does it look like? So this you can do using various inverse scattering methods. And in fact, it doesn't stop here. You can actually construct a large chain where you alternate the charges. But constructing the solution in this case is dramatically much more complex, but we have a machine that can build it for you. To sort of show you that we actually did some work, this is what the spacetime looks like. You can explicitly write it down on paper and plug it into a computer and plug it into the paper. It's not a numerical solution, it's an explicit solution that we can construct. Okay, so let me tell you some properties of this guy. First, for my stringy friends, you can uplift these class of solutions in string theory and ask what do they do. Right? So there is a limit where you, for example, take the outer rods and collapse them to points. That's an extremal limit. And when you do that, what you get is a bound state of a D1, D5 extremal black holes sitting on the north and the south pole. So you can actually explicitly construct bound states of brains and antibrains with themselves. And you have this brain and an antibrain, which are sitting on top of bubbles that stay stable.
Why is it stable?
Actually, it is not stable, and I can tell you many reasons why it shouldn't be stable. So the first, you might say that, oh, if you have this, why doesn't it just tip over, right? So that picture is actually, that intuition you might think is correct, but it's not quite. First, as I was saying, that if you come into these regions, they just blow up into these extreme things. So actually the distance between here and here is very, very large. If you study these solutions more carefully, there's something very weird happening. So in this limit here, where I collapse the rod, it becomes an extremal black hole with an infinite throat. So I'll describe this. So actually, this Witten bubble of nothing that's sitting in between wants to expand, but it's expanding inside this black hole to its singularity. There's this very weird thing where you have a bubble of nothing that is expanding, but it's expanding into this singular point. Okay? So the intuition that might just tell you, oh, I can just tip this over, it should fall apart, or to say, oh, I have a bubble of nothing, it should explode. Actually, that gets immediately ruled out. But there could be other instabilities which requires to check the full system, which is a very hard PDE, which we're working on now. So we should expect some instability, and that should be interesting, and I can tell you more about it. Right? But the obvious instabilities aren't. You can see that they're not going to be there. So okay, here is the picture that I was trying to tell you. So one thing you can try to do to characterize that specific one is you can plot the redshift factor. Right? You can look at the redshift factor it's a measure of how strong the gravitational field is. So if you just have the tree bubble, you get basically you get a redshift factor. So around, on the surface, you get very large redshift, which is given by the mass over in units of the compact direction. So if you make the mass very large, which you can dial independently from the compact direction, so you can make this have very high redshift. And then as you push these points to their extremal limit, you get this sort of fang object where you get something that is smooth by high redshift, and then you get infinite throats that open up at the poles, right? And in this infinite throat, this expanding bubble in the middle is expanding inside those infinite throats.
You were mentioning the connection with the D1 pi system, at least in the limit. So then your parameters should be related to the number of 5 brains and one strings or something, right?
Yeah, you can compute that.
Which is the relation? So it's related to this, what you call M here? Or?
Yes, so the mass, yes, so the M is going to depend on the charge of all of these things, and this D1, D5 charge. So here, when we go back here, there are these charges in the system, which basically the point is that, so over here I had a rod, which I shrink, and on that rod I had flux. But you take this limit of taking the 0 rod size while fixing the flux, so we can make this limit precise, and then that flux that gets left over becomes the D1, D5 charge.
So we expect this in the quantum theory, this M to be quantized. Parameter you had before.
Yes, but it's going to be quantized in units that are much, much smaller. It's quantized, but it's quantized in units. You know, it's like saying something is quantized in Planck units. But it also gives you another perspective that these bubbles, you can think of them really, their origin as coming from D brains that are non-supersymmetric, that are puffing up in some funny way. Right? So these are like D brain configurations that are coherent to be approximated by
Last question on this. M appears as when you solve the equations, appears as an integration constant that can be associated to a charge of these fields.
So
or
M
is really the ADM mass.
M is really the ADM mass. So you construct this solution, you can Toulouse-Acquin and reduce it to 4 dimensions. You can compute the ADM mass. So that would be the effective mass that you would observe far away, and it's really the ADM mass. And then you can look at various limits of these monsters. Okay, so one way to characterize them is to just see what is the redshift doing. So this allows you to know something, how deep is the gravitational well of these objects as you approach them. So up to basically coming in here, it becomes very much indistinguishable, unlike a black hole. Okay. And in fact, so even this specific model where you have 3 bubbles, they still have this bag-end structure. And they have an effective size where they open up, which is like 1.52, their Schwarzschild radius. So they're very, very compact objects. Any questions? Okay, so one of the other things you can do to try to characterize this, and this goes to your question earlier, Martin, is that what we can do, at least so this is I showed you the metric. It's a very complicated, messy thing. Try to solve geodesic equations in this background, and good luck. But what we can do is the following thing, is let's take the global sphere. Suppose I'm sitting over here and the object is somewhere in the middle. What you can do is you can imagine at the back of the sphere, you're shooting light rays that you then observe here. Right? So the question is then, what would this look like in the sky if you were to do something like that? So we can go ahead and do this. This is in collaboration with Emmanuel Berti and Pierre. Well, Pierre went and did this. This is the first time I did any work that required a cluster. I'm very proud of that. So you put some emitter back here, and you can shoot 10 to the 6 light rays and ask, what do you see over here? So in flat space, you just see the back screen. Okay. If I were to put a black hole over here, what you would see is something like this, where you have the dark region. Then you have a part of the green light here that would come, but then get lensed around, so they show up over here. You also you have something similar happening to the blue and something similar happening to the red, where a light ray comes and then it gets lensed around.
Did you explain what this means? This is like a 2D slice, and the colors are just.
So can you see this cone thing here?
Yeah.
Good. So this cone thing here, right, this is a slice here, which is what I'm putting there, right? So I'm sitting in the back here, somebody is sitting in the back here, and at every point here, it's just shooting light rays. These are geodesics. So you can set that up on a computer. So in flat space, if you don't have anything, you just see the light rays coming, right? So you see the red, the green, and the blue.
The emitter is shooting out those 4 colors. So,
Yeah.
In different directions.
It would be bad to say the color of the light because the other redshift factors. So the color coding is just showing where the light is coming, which quadrant of the sky is coming. Okay, so the color coding is just saying which direction.
So the point on the front surface is the observer.
Yes. So
Right? And the observer can look in a different directions, and you see where the geodesic lands.
that's right. That's right. So the point. This is the observer sitting here, and the object is the star is sitting in the middle, and there is a background. So it's there, and then it's seeing the light that's coming directly at it from the background. So flat space, nothing happens. If I put a Schwarzschild black hole in the middle, there will be a region where, this black hole. But then you get lensing effects like this. Okay. Good. So you can ask, what happens if I do this for this Schwarzschild black hole, for this new solutions that I'm constructing? So this is a sort of top view. So, I had these 3 bubbles. So if I were to look at, if the orientation of that 3 bubble is that it's facing me this way, this is what you see, for example. Meaning the light rays that are coming from the back, there is an extreme one, but then there is some that sort of get trapped inside and then get matched around in a very, very, very chaotic way, and then at some point come out. This is these fringes that you see, like it's very spread out. It's just this very chaotic behavior of this light ray from the back that just gets moved, and they sort of do a very crazy. They visit this structure in a very crazy way, and at some point come out, and the information about their orientation is forgotten.
There's a time delay.
There's a time delay. And then here is, if I'm looking at it at pi/2, so you get the dipole structure, because this is a dipole. And then if you were to rotate it a little bit, you get a structure like that. So it becomes even messy. So one of the interesting things that was rather surprising, so when we constructed this geometry, it has, like, the mouth, when it opens up into this crazy bag end structure, it's 1.5 times the Schwarzschild radius. The space-time around there is very funky. There's no reason, it's approximated by this other geometry, which does not look like Schwarzschild or anything. So so if you look at this radius where it becomes very, very dark, is more or less exactly the same radius here. So if I were to observe this versus that in the sky, and I couldn't say see in the middle, just by looking at the place where the light dips, it's indistinguishable from a Schwarzschild, even though the metric in this thing is very, very different from a Schwarzschild. So this was very much a surprise, right? So, we characterize this, we know the thing that we look like. There isn't any sense by which I can take a limit and call it a Schwarzschild black hole, except very, very far away where I only measure a mass. But somehow, if I shine light, the light ray tells you that there is a very sharp line where it more or less looks like a Schwarzschild.
Is that because the radial potential for these geodesics looks more or less like Schwarzschild until you get to the photon sphere?
Exactly. That's effectively what's happening. So if I just look at there's a subtlety of when I construct a potential. There's a great deal of dependence of coordinates of the radius. So there's a game you have to play.
Yeah.
So the system doesn't, because it's actually symmetric, you don't technically have a good definition of a radial coordinate. Yeah. Right. So there are all of the subtleties. So there isn't even a sensible way by which you can say that, oh, I take the potential, then I expand and say this. I need to somehow be able to fix what I mean by the radius far away, but then that can get corrections in angles. There's all sorts of details about that. So the question was, you have this rather messy thing, how could you just start to characterize and compare if geodesics? Geodesics are exact observables, so you can just see. So you start to see that, so this rather extreme, chaotic behavior is quite interesting, and it just starts to characterize what something new could look like. Right?
So if I had a neutron star that's almost a black hole, that would look kind of like.
That could look like that, yes. That's right. But a neutron star has a size which is ordered to twice the Schwarzschild radius. The neutron star is even bigger than the photon sphere, right? Which is 3.5 times.
But I still get those panels with a strong reflection, or?
Yes, you should. You should get a version of this. The thing that I'm calling into doubt is the light ring. So this radius here is the light ring of the black hole. It's just slightly larger than the Schwarzschild ring. So this object is so compact that the outer light ring that you would see is exactly the same as that. So there should be a good effective field theory explanation of why this. There should be a good effective field theory explanation that tells you that if you have something that is sufficiently compact, then its light ring should be the same given as Schwarzschild. There should be an effective field theory explanation, which I cannot make sure.
I mean, so the geodesics are very nice to look at, but like for instance with LIGO, the thing that really matters is the effective potential near the light ring, which here there's some modification. It sounds like.
Yes, but it's very tiny. So at LIGO, what you would want to have, if you understand this effective potential, what you want to know is the quasi-normal modes, right, as they go up. So that the lowest level just gives you the mass. The next one will give you a mass and a charge. But anything higher will actually start to probe the structure, right? So we're now computing, like trying to understand the quasi-normal modes of this. In the simplest case, there's actually a paper ready to explain the quasi-normal modes of these guys. Actually, I do not describe this. The simplest one is just a bubble with some charge. So that turned out to be incredibly rich. Yeah, so the first sign that we would get from LIGO that there is something new is when we start to measure these higher modes. And this is very interesting, and I think you should be very excited. We're not going to be able to see it now, right? So LIGO now is at Q at 8+, and in the next, there'll be an extra room to 8++. Then there'll be some upgrades, and then there is the Einstein telescope that's going up. There's the Cosmic Explorer that's going up. These are each have their arm 10 to 20 times larger than LIGO, and those will be up by 2035. Those are going to measure quasi-normal modes of compact objects.
The lowest one agrees.
Well, that's exactly the point. What I'm saying is the fact that the lowest one is just being controlled by the light ring over here. So for this solution, we can't compute it yet because these are highly nonlinear PDEs, and we don't know, we don't have a systematic way to do it. But I would expect them to agree because the lowest mode just gives you the mass.
But no, but it gives you, there's the radius, which gives you the orbital time, and then there's the second derivative, which gives you the imaginary part of the pleasant and whatnot, right? Which
Yes.
is decay.
Yes, but that information, I think so far is more or less degenerate from the initial data of the mass and the spin. Right? It doesn't give you more information than that.
Well, you can easily measure those two things, right? Because you can measure the spacing between the peaks and you can measure the rate at which they decay.
That's right.
So I'm just asking if this agrees with that for the same mass. Because it's not, I mean, given that you have a modification of that scale.
I haven't computed a quasi-normal mode, so I cannot answer. Okay. But the answer that I was saying is that I would because those lowest modes are degenerate with the mass and the angular momentum.
Yeah.
Right. If I construct a soliton of the same mass and charge, as I would observe, that wouldn't tell me I have something new. That's the statement. Right. I need the higher modes to be able to distinguish, black hole, the genuine GR black hole versus something.
There's also people looking for echoes, which are signals that show up later.
Yeah.
If you have this time.
So these will have echoes. Right. Precisely, the echoes you can just think of as modes. The echoes should have this sort of chaotic behavior. You can think of as modes that go in, the sample, and come out. Black holes don't have echoes because it just goes into the. Yeah. So like I showed you what the metric looks like. So trying to compute the Topological equations and just compute this is a mess. So far, we think we can control it if we look at scalar quasi-normal modes, but even that is hard. Okay. So there's prettier pictures here. So you can ask, what is the lensing? So you can also do the same thing where you put at the background just some sky, then you get some rather nice, interesting lensing structure, but still the same sort of chaotic behavior. And the last sort of picture I'll show you, which is interesting. So suppose you had some accretion disk, and then if you put an accretion disk around a black hole, there's the line, and there's the sharp decay of the light. So if you were to put an accretion disk around one of these things, you still get some structure that comes out from inside, if you're able to. One of the fun things that you see is that although this light is coming out, they get their luminosity is further suppressed by the redshift factor, and that redshift factor could be, I showed you the plot of the redshift of those things. So the redshift further suppresses these things. So if we actually even go into imaging telescope, the imaging of a black hole, you should actually see completely dark in the middle. But if there is something else that's not a black hole, at some point you will see the light inside. So this sort of a plot is to sort of indicate what those things could look like. Okay. So I think now I'm at the end. So there's various things that I didn't tell you about, which are also equally exciting. So we can study these solitons in ADS spacetimes. Why? So that we can actually understand what are the quantum degrees of freedom that they correspond to. There's very interesting questions about both stability, existence, and are there actually real world mechanisms that can create these objects? There's many other interesting questions. What is the full phase space of these coherent configurations? What is the spectrum? So something that I didn't highlight, right? The mass scale of these objects go from the Planck mass all the way up to whatever mass that you have. There's more to exploit about the integrability. There's very interesting questions about non-SUSY bound states of Z-brains that you can study. And from this perspective, since these things could be, they can have Planck mass scale, there's a dark matter paper to be written, and I will write it when I get tenure. So, the day that I get tenure is the day the paper will appear in the archive. I think I have more or less have it, but you can ask me questions about that too.
me, the first question about this subject is stability. For BPS, we know that they are stable.
Very good.
But,
Yeah.
How do you?
Good. So, depending how much patience people have, there's a whole set of slides about it. So the place where we can study the stability is like, so the simplest bubble, which is strictly symmetric. Here you can try to ask, what is the stability property? As I just mentioned, this is really the Witten bubble of nothing with charge turned on to it. So you can write down actually the metric for that quite explicitly. There's a reason why I will say where I have this picture, and it will make sense in a moment. You can write down this metric very explicitly to show you this bubbling structure. You have this is in 5 dimensions, not in 60. You have the extra circle, then you have the time. So you just have these warp factors that are just the Schwarzschild standard warp factors, and these 2 parameters, RS and RB. The bubble that we want occurs here, right? When RS is smaller than RB, you get a bubbling structure. When RS is greater than RB, you get actually a black hole. So you have this phase-phase. Just for a single bubble. You can compute the masses exactly. And one of the key things that you see here, I promise this is related to your question, is, k equal to, so there is a parameter k, which is an additional topological number. Don't mind that. But when k equal to 1 here, there is a bound of when this solution exists, which you can read off from the charge, meaning that the radius of the bubble is bounded, the diameter of the bubble is bounded above by the radius of the extra dimensions. If I want to have small extra dimensions, then these are very small compact objects. These are very, very tiny objects. So we call this topological part. So for that guy, I can study stabilities of it very nicely. So you can, I can even be more sharp. I didn't realize I had all of these slides, I'm sorry. So suppose you make the extra dimension to be just like 10 times the string scale, which is about 1,000 times the Planck scale. Then the mass of this object is like 10 to the 11 proton mass, but its size is far more compact, 10 to the minus 3. So this is like an ultra compact particle that you would have. And what you can do, you can compute the gravitational action of this object. You can compute the gravitational action of the black hole region, and also the Euclidean action of the bubble. And let's plot it. We get a plot like that. Okay. So what this plot is showing you is that you have this point, which is so when I turn on the charge, the phase space splits into 2 solutions. The original one was the Witten bubble of nothing, which was unstable, which is sitting here. But then you also have a valley down here that gives you a metastable state, right, which lives in this image. So for the single bubble, you can explicitly check and see that it is metastable. And one of the fun things about this is that you can then compare these actions and ask, you can compare a black hole here with a bubble here, which live in the same ensemble. And then what you actually find is that when you are at large temperatures, right, so you can, at a large temperature of a bath, whenever you have these bubbles, they decay to some black string, they become black holes. But if the temperature of the bath is small enough, what you actually find, black strings become bubbles, and in doing so, emit a lot of entropy. So this is where the dark matter model begins. Because what it is saying is that, you can have a lot of primordial black hole, which we would typically expect to decay by Hawking radiation. But if these things are there, then this is another channel where primordial black holes can decay to this bubbling structure, and they can live more long. So studying the stability allows us to say something about what small versions of these things can do.
Say that they are long-lived, even though they have an extra channel to decay to?
Meaning, at least, so they could be other things that this bubble can decay to, maybe some more complicated bubbling structure, but but there's no black holes that they can decay to. There's no black hole that they can decay to, but they might be able to decay. So one thing that we expect to be able to do is, we have these things, you have these bubbles, they're fairly symmetric. You can ask a related question, which is if you dump energy into this thing, what should it do? Does it blow it up? Can it absorb it? And if it does, what should happen? What we expect to happen is that if you start dumping energy with it, this thing should have wiggles, should have modes on top of this bubbling structure. There's a larger phase space that should exist, which just corresponds to wiggling these things. That should describe what happens when you dump energy.
Do you mind going back to those beautiful multicolored images?
This one?
Just a little easier for me to understand the previous one, where it's just the 4 colors. Yeah, I was curious, kind of continuing with your analogy of viewing this as like a 2D phase space. There's chaotic regions of these trajectories, but it also looks like there's still some integrable slices, maybe one would call them, or these cycles where the image is preserved.
Yeah. So this is the fact that this thing have a dipole structure, right? So that's why you see things too low, just that there's a dipole. I mean, it's a dipole. But if I make it sufficiently complicated, this dipole thing should also disappear. Yeah.
So how do you mean sufficiently complicated?
So yeah, it's because the space-time is actually symmetric, right? So it's to characterize an actually symmetric, you have the dipole.
If these are real objects and they live and they're okay.
Yeah.
Well, my question maybe still stands, which is, is there maybe some way of understanding these from the nice solutions you constructed based off just the integrability of the?
I showed you what the metric looked like. I could not compute the geodetics by hand to see this. In fact, the fact that the geodetic solutions are so chaotic is exactly the point that I shouldn't be able to compute it by hand. Maybe I might be able to get the outer ones, but the ones that actually probe the structure, they're just bouncing around. Because remember, these bubbles, when it hits it, it sort of bounces, but then it bounces and it does some other configuration, some flowery configuration and around, and then at some point come out.
Yeah, I guess I'm not saying you should be able to understand the chaotic regions of that image, but maybe the nice ones, I'm just curious, maybe they're somehow connected to the...
Good. So the nice one outside I should by looking at this approximated metric. Yeah. But even there, it's still a second order PDE, but you can solve it, yes. Another thing you can do more sharply, which is important, is there is a way to characterize geodesics along complex objects or on short shield or anything by looking at their Lyapunov exponent. So if you come near the light ring, you ask when you shoot two geodesics, what is the Lyapunov exponent? You can compute this. So there are various characterizations like that. So if you compute it for the short shield, you get some number. You compute it for these objects, for the outer ring, it's the same. So there's some quantitative things we can do.
And so there should be some points where this Lyapunov exponent goes to 0 or something to get these nice structures that still appear?
Not necessarily 0, just not defined. Because there's no chaotic behavior. So the Lyapunov exponent is that at the light ring is an instability period where if you take two things and you shift them a little bit, they go off. Right. So there I can define a Lyapunov exponent.
Right. Yeah, I'm just saying that there's okay. Anyways, there's parts where they don't diverge, right? Interior, that's all I mean.
Yes, you're right. So the geodetics here and here and here, those are computable.
When you have multiple reflections in a very symmetric system, droplet of water, you also have caustics. So
yes.
Here I don't see any, or are there?
I think you can sort of think of the inside rims like that as caustics, right? Because caustics is really at a place where things would focus. It's like a focusing region. So light rings, technically, you can think of them as that, right? It's a focusing region which you can associate with a sign, right? You can have. So you can think of these caustics here as just showing you this thing is actually.
Oh, just the method you use of shooting the light rays out from the observer is what the strong lensing community does to reconstruct the So did you use their codes or okay?
No, I didn't do it. Pierre is pretty amazing. So he actually did it all in Mathematica. So he set it up. He set the problem up in Mathematica, troubleshoot it after a while, and then just then at some point just moved to the cluster at Hopkins. At some point, he was using all the nodes.
Because I've been looking into how these things work, and I think of like maybe 10 years ago there was a breakthrough in doing it faster, where they don't shoot out individual light rays, they shoot out kind of polygons and see how the polygon deforms, because they need to do it much faster given all the surveys coming up. I mean, I think those codes might be extendable to your.
So at some point we looked at those codes. The big issue is that they're designed for 4D systems with very few things. But these are technically 6D systems. In 4D, where you do the computation, the metric is much more complicated. There are additional modes that you need to account for. But those codes don't immediately. They don't.
They probably use Newtonian approximation.
So initially. This paper is with Emmanuel. Initially, we were talking with one of his postdocs, and who does this imaging thing. You know, she showed us a few tricks, but then we realized that those codes we couldn't immediately import it to study geodesics in this case. But you know, then Pierre just spent like maybe 2 weeks, several weeks, just build the code in Mathematica from the bottom up. But of course, it's incredibly inefficient. The first round, he would make a picture. It would take several days to run on the computer. And at some point, I told him there's a cluster node which you can use. And then we moved there, and then that's when we could scale it to that large number.
Thank you all again.